So next up, we have Alicia Curth, who will be doing a presentation on personalized therapeutics. Alicia is a PhD student who also joined our lab last year. Alicia, please go ahead and share your screen if you're ready.
Yes, great. Hi, my name is Alicia. I have just finished my first year with Mihaela. And over the last year, we worked on the topic of estimating heterogeneous treatment effects, which is obviously a very important part of developing personalized therapeutics or selecting the best treatment for any individual. In this talk, I'm going to cover quite some work. So this is basically a year of work that we're covering here, so it will be quite high level. If you're interested, I invite you to afterwards check out the separate papers in more detail, or to contact me for more detail on the separate things. I assume a little bit of background knowledge on the potential outcomes framework in this talk, but I'm giving a quick overview here. So basically, we're considering the kind of basic setup of heterogeneous binary treatment effect estimation within the potential outcomes framework. We assume that each subject has some features X, two potential outcomes associated with having been given a binary treatment, the binary treatment itself, which is assigned according to some propensity score, and an actual factual or observed outcome, which is corresponding to the treatment, to the outcome, the potential outcome of the treatment that was actually given. The quantity that we're interested in here is the so-called conditional average treatment effect, or CATE, which is the expected value of the difference between the two potential outcomes given treatment and not given treatment. This quantity is identifiable via the potential outcome regressions if overlap and unconfoundedness hold. The machine learning literature over the last 5 years has been very interested in this problem and has made lots of progress in the settings of binary treatments, but also multiple treatments, continuous treatments, and much more. And our lab has been quite at the forefront of that. The current focus up till now has been on handling observed confounding and observational data. And that's basically because there's a challenge as treatment selection on observables leads to differences in covariate distributions across the two treatment groups. Many solutions have been proposed over the last 5 years, most prominently balancing or domain adversarial representations, propensity weighting, and propensity dropout. What we looked at over the last year was a different focus, namely how to best model the treatment effect itself. That is because even in the absence of all confounding, so when the two distributions are the same, CATE estimation is non-trivial. That's because the label that you're interested in, so the difference between an treated and an untreated individual, is never observed. That's the fundamental problem of causal inference. Of course, there's a very simple solution to this, which we also call the indirect approach, or which you might know as the virtual twin or T-learner type approach. Which is to not model the treatment effect, but to model the potential outcomes separately, and then use their difference as the CATE estimate. However, when the potential outcomes are very complex relative to the treatment effect, targeting the simpler function, which is the treatment effect, might be much more efficient. So in this picture that you see here, the red and the blue curve are the two potential outcomes. And you can see that both of these functions are quite complex, whereas the treatment effect is a simple linear function. So if you could target that directly, that would be much simpler to estimate. Or to speak in more medical terms, when there's more prognostic information than predictive information, this might be a good approach to target the treatment effect directly. Therefore, we investigated two types of strategies over the last year, which I'm going to talk about in turn now. The first one is a model-agnostic multi-stage approach, and the second one is to modify inductive biases in end-to-end learning strategies. So the first approach we looked at was in an AI stats paper, is to look at meta-learners. And meta-learners are model-agnostic algorithms that provide something like a recipe for estimating treatment effects using any machine learning method. There's two very generic approaches for this. The first one is what I just talked about, namely the one-step plugin or indirect learner, which simply estimates CATE as the difference between two functions. The second, more sophisticated approach would be what we call two-step direct learners, which find some kind of a surrogate for the potential outcomes contrast and target the treatment effect directly. And that's possible even though the contrast is unobserved, because we can construct some kind of pseudo outcomes using two-stage algorithms which impute some parameters And these pseudo outcomes have the same expected value as the treatment effect. And you can use these pseudo outcomes and regress them on X directly. I don't have the time to go into what exactly they are. But what I can tell you that if the treatment effect is simpler, that is, for example, smoother or sparser, than the potential outcome regressions, such two-step learners have a clear advantage theoretically, which is what we show and investigate in this paper. After we showed this, we asked ourselves some new questions, namely, can we improve indirect learners by simply imposing our knowledge that Kate may be simpler than the potential outcome functions? And can we do so in some kind of an end-to-end manner to match or even improve upon the performance of such direct meta-learners? And in our recent NeurIPS paper, we looked at this and came up with some solutions, namely 3 strategies based on neural networks, one which is based on changing the regularization scheme, one that's based on reparametrization, and one that's based on a flexible multitask architecture that kind of learns what to share between the potential outcome functions. And in this paper, we found that all these strategies can indeed improve upon the baseline indirect learners, and some can match the performance of direct learners. To evaluate this, we conducted many empirical simulation studies. In particular, we looked at many semi-synthetic simulations where we were able to vary relevant experimental nodes. Even though we did discuss in a recent paper that there are quite some shortcomings of using such semi-synthetic data instead of real data, such semi-synthetic studies can still be very insightful because you learn in which scenarios different methods perform better and why. All learning strategies that we considered were implemented using neural networks, and we mainly focused on the relative performance based on root mean squared error of estimating the treatment effect function. Here I just show an example of the results that we found, and it's too much to discuss in detail now, but what you can see in each of these plots, there's a blue line on top. That is the vanilla, simple indirect learner. And all the strategies that we considered are the other colors that are performing quite a lot better across different simulations. Finally, at the end of the year, we also considered a new problem, namely treatment effects in survival data. That is because the majority of the machine learning literature on treatment effects considers continuous or binary outcomes. So we were wondering what makes heterogeneous treatment effect estimation from time to event data special. So in a recent NeurIPS paper that we wrote together with Chunky, who just graduated our lab, we focused on the problem of learning treatment-specific conditional hazard functions. And we found that unique challenges arise in this context due to a variety of covariate shift issues that are combinations of confounding, censoring, and what we call event-induced covariate shift. We theoretically analyzed these effects and proposed a new deep learning architecture, which we call Servite, based on our insights. And we found in this paper that our methods indeed outperforms baseline by correctly addressing covariate shifts from various sources. If you're interested in any of these papers, you can find them here. All of these papers are already available online with the exception of Servite, which will follow soon. And to replicate any of the experiments that I've conducted on binary treatment effects with standard outcome data, you can check out KateNets, which is a repo on my GitHub. Finally, if you want to learn more on individualized treatment effect inference more generally, because we've definitely done, or the lab has definitely done more work than what I've presented now, please do check out the research pillar on our website. Thank you so much for your attention.